Hi guys, this is another video lesson, and this one's going to be on vector and scalar addition. Now fortunately, half of this video isn't really necessary. So let's talk about the half that we don't need to worry about, which is scalar addition. Because as we already learned, scalar is just a fancy term for quantity, some kind of number. So scalar addition is just addition. If I have a couple, say, distances, which distances are scalar, they're just a how much. So distance 1 equals, say, 4 meters, and distance 2 equals 7 meters, and distance 3 equals 8 meters. If I said, well, add up all the distances, it's just 4 plus 7 plus 8. 11, 19, my total distance. It's very, very easy. Scalar subtraction, same thing. But what if I went a distance 1 and a distance 2 and added them together, and then wanted to take away distance 3? What would I have? 4 plus 7 is 11, minus 8 is 3. This is easy, so let's skip it. Well, let's really worry about this, vector addition. So as we already talked about, vectors are kind of like scalars, except one big key difference. Scalars are just a how much, a number, and vectors are a how much, so a number, plus you also get a direction, some kind of direction. So for instance, if I were to say, I ran 3 miles, that's a scalar, it's just a how much. If I said I ran 3 miles north, that's a number and a direction. Now the reason we have to do these additions separately is because when I want to talk about a total displacement, so, where did I end up from where I started, I can take a whole bunch of different terms. Let's say I went a couple different displacements. I have a couple different displacements on my journey. So the first displacement, delta x1 equals 4 meters. And the second displacement, delta x2 equals 7 meters. And the third displacement, delta x3, is 8 meters. Well, at first glance, it looks the same as distances. But if you think about it, it's completely different. Let's say I went for a run, and I went 4 meters this way. We'll call that east. And then I also went 7 more meters this way, east. And then I went 8 more meters this way, east. Well, in that case, we would just add them right up, because I was always going in the same direction. But what happens if instead of going 7 meters east, I went 7 meters west? Now we get a problem. Because isn't 7 meters west kind of the same thing as negative 7 meters east? Well, if so, what I can do is subtract these. The problem is, I can still write this as 7 meters to the west. I don't necessarily have to put the negative sign. So we have to have a good way of figuring out how to make sure we add or subtract at the right time. So the method we usually use is what we call the tail-to-tip method, which means let's draw this journey, and we'll always draw the tail of one vector starting at the tip of the first one. So here's our starting point for this journey. Point A. Displacement 1 is 4 meters over. Well, now we're going to go 7 meters backwards. And instead of going back to A and drawing it, I'm going to start from where I left off. And if you think about it, this makes sense. You don't go for a run and then say, well, I'm going to turn now and go all the way back to your starting point, then turn and run a different direction. What you do is you go for a run, and then you turn from your current position and keep running. So I started at my house, I ran 4 meters east, and then I decided I was going to turn completely around and run 7 meters west. Well, now we have this last vector, 8 meters, going east again. I'm going to start with the tip of the last arrow I drew. My tail will begin there, and I'll go 8 meters the other way. Now, if we had a big grid on this paper or on this wall, 1, 2, 3, we know we originally went 4 meters over, and then we went -7, so this should really be at -3 meters from where we started. And then it went forward 8. So in total, I'm at +4 meters. I'm going 4 meters in the east direction. Now, this is kind of a lame example, because we typically won't really look at vectors that are just east and west. They're pretty easy to add up. We don't really need a fancy method for working with them. What we do need a fancy method for, like the tail to tip method, is when we have arrows that aren't just east and west, when they look more like this. Maybe 4 meters up this direction, and 7 meters down like that, and 8 meters maybe slightly off like this. Now, when we have these arrows, we probably want to have a quantity to go with it, maybe an angle. So let's call this, say, θ3, and we'll call this θ2, and we'll call this θ1. Let's use the tail to tip method again, and we'll use these arrows instead. And we'll first get all this junky junk out of the way. So we're going to start at point A again, and we're going to go to the first part of our journey. 4 meters up at an angle. And that angle was θ1. Well, if we wanted to figure out how far over I went and how far up I went, we'd use some simple trigonometry. We call the length of this line delta x1, and we would call the displacement this direction, so right here, we would say, well, hey, that's just delta x1 times the sine of θ1. Down here, this little piece would be delta x1 times the cosine of θ1. Now, I don't know about you, I have trouble remembering these sometimes, so I have a little system. And not that SOHCAHTOA thing that everybody else always says. Doesn't it look kind of like an eyeball? I mean, if I drew a little pupil here, it looks like someone who's half asleep. So I pretend that theta is an eyeball, and theta is looking this way. You see the sine. The sine's vertical. I see the sine. It's across from theta. Cosine is always with theta. Think about collaborating in a cooperative cohort for a company. Co means together. Cosine is with the angle, and you look at the sine. Okay, so what have we done so far? We figured out that I can get a x-axis and a y-axis value for this. But we're talking about vector addition, not just vector breaking down. So where do we go from here? Well, we follow the tail to tip method. We went on the first part of our journey, and now we're going to do the second part. x2 goes 7 meters like this, with an angle θ2. We could figure out how far over, and we could figure out how far up again, using sine and cosine. Then finally, the last part of our journey goes over at kind of steep at some angle, θ3. And we could figure out the x and the y. In fact, what we would do is, if we really wanted to figure out what we call the resultant vector, the kind of net displacement, which was this starting point to that ending point, which in this picture happens to look perfectly vertical, but that's just a coincidence. Here's my total displacement. Let's call this delta x total. In order to find that, I need two things. I need to know my total displacement this way and my total displacement this way. So I'd have to get the x component for 1 and the y component for 1 and the x component for 2 and the y component for 2 and the x component for 3 and the y component for 3. Now, why do we need all those? Well, the same reason that our first problem was really easy. If you're going forward and backward on the same line, it's just simple addition and subtraction. So we can make a table, our x's and our y's, and we can put x1 x2 and x3 in this side, y1, y2, y3 on this side. Let's see if they should be positive or negative. Well, let's call this direction positive and up positive. x1 is a positive, x2 is a positive, x3 is a negative. y1 is a positive, y2 is a negative, y3 is a negative. Now we just add them up. The total displacement in the x direction is x1 plus x2 minus x3. The total displacement in the y direction is y1 minus y2 minus y3. And then finally, our actual total displacement, and by the way, I shouldn't have used x's all over the place, I know that's a little confusing, is simple. It's a triangle. This triangle, I'll exaggerate the angle here a little bit. If this is our total displacement, we say, well, hey, this can be drawn as a triangle too. Where this is our total x, this is our total y. And if we wanted to find out that value, all we need to do is use the Pythagorean theorem. If we wanted to get, say, that angle, the total angle, we could use an inverse tangent. That's it. You guys should already know trig, but if you need more help with that, come talk to me and we'll go over it. That's vector addition. Bye now.